Oh, hi, good morning. Let's start our meeting. I wanted to welcome all of you to this session, and I hope that all of you are having a great summer. I know it's summer is a fun time for the family, but I appreciate that you're putting the effort to improve your career, and I'll be very happy to help you in improving your design skills. So my idea is to put together kind of review sessions, sessions in which we will be able to communicate, provide coherence for the online class. As you know, that every one of you is maybe in a different state and different location, and very difficult to communicate. So the Saturday session is going to provide a little bit of cohesion and will give us review. And the way that I'm going to proceed with it is that I will make a recording of the session, because I realized that some students are actually on the East Coast and they have difficulties kind of attending the session in real time. So I'll record the session and put it online for those who are not going to be able to come to the review. Although I said that it is mandatory, but there is no points associated with not being able to attend. It is encouraged that all of you will be here, and I like to encourage kind of cross communication between team members, especially for the projects. So what I'll do is today I'm going to introduce the topics that we will cover, go over what's happening in the class website, discuss the projects, and I wanted to hear from you about the projects especially, and I wanted to be able to form teams of 2 members to work together on the 2 projects. And then I'll maybe review just a couple of areas related to the material that we covered in the first week, and prepare you for the next week. So I'll share the screen with you and look at the schedule that we have. As you can see here, the schedule is started already this last week. So this is our first week of classes. And in the first view, you notice that the class material is going to be in about 3 sections. The first section is to review, for those of you who have not the courses taken very recently, especially, to review for you the main ideas for stress analysis and deflection. So what you'll see in the first part of the course after this week, so this week is basically on materials and material selection. You'll get just a preliminary idea about how to select materials for stiffness especially, or for deflection. But in general, in the future, if you're going to take the next class, 296B, you will be doing more material selection for high temperature applications. So anyway, so the first week is just on materials, and then we'll get into a portion of the class on a review of stress and strain and deflection. So that's going to be the next 2 weeks or so. And then you will get into application of stress and strain and deflection into failure in static configurations. So if you have a static load, we want to assess all of the failure mechanisms and determine the factor of safety. And that would be important to apply in our design projects. So this is the second section. The third is going to be on fatigue analysis, because this is going to be a very important part in the design of connecting rods and in the design of power transmission systems, which is the subject of this class. So fatigue analysis will occupy maybe 2.5 weeks of our time, and you will see that coming in towards the first week and second week of August timeframe. And then the last part of the class is basically the application of all of that. And the application is going to be on the design of power transmission shafting and all of what's connected to the shafts to transmit power, namely gears, pulleys, shoulders of the shafts, pins, connect all of the elements that are related to the transmission of power will be there. So that part is intimately related to the second project, which we will do also as a team. And the second project is designing aspects of a gearbox. So we know the gearboxes are very important in power transmission. And the second project, which will be based on the last, or will be in parallel to the last 2 weeks of the class, will be just on that. So it's be a long homework assignment, essentially, to start designing a shaft and all of the gears, and then how you transmit the power in a particular application that is specified for you. So that's kind of an overview on the philosophy of that of this course. And as you know now, it's material selection, stress strain, static failure, fatigue failure, and then applications to shafting and power transmission in general. So this is the structure, and as you can see, we'll have a midterm exam on July 29th, and I corrected the dates. So this is the correct date here, from 1 to 3 p.m. Some of you will be able to come to campus, but many others will have to take that exam on site, on some site, and then you have a proctor who will send us your answers. And then the final exam is on the 2nd of September. Now let's discuss the type of grading that we have. And what we will do is that we're going to have a few homework assignments up to 7. So at this point, we have 7 homework assignments, which means that we have the last 3 weeks without a homework assignment for a particular reason. So the 7 homework assignments will be directly from the material that is covered in the videos and recorded online, and we will review some of that on Saturdays together. Then the midterm is 15% of the grade. And then we put significant emphasis on design projects. So we have one design project that is big. So this is the main design project. And this design project is the design of a connecting rod of an internal combustion engine. So you will be asked to select a car engine of your choice. And then this car engine will have specifications in terms of horsepower and torque. And from these specifications, you'll be able to select or start designing a connecting rod for that particular engine that you have chosen. As I mentioned, this will be a long project, so it's going to start essentially from this coming week. And we will work from a manual. We have a manual online, and this manual is being updated by Andrew Sheng, who's the TA. And the manual goes through steps in this project that I will discuss also here if we have the time. So that project, the idea is that it is a comprehensive way to design a typical component in an automotive application. So that goes from application of understanding of stress and strain and material failure and fatigue failure to using modern tools of design. Namely, we will have software. The software is going to start from SolidWorks, and then we would do solid modeling, and we'll be able to utilize MATLAB to do some additional calculations with code that we have partly written for you. And then we would use COMSOL, which is a multi-physics platform, finite element platform, to implement the design. And finally, if we progress rapidly through the project, we'll have enough time towards the end to use Abacus, which is also an additional piece of software that is commercially available to do three-dimensional analysis on the connecting rod. So as you will see here, that the idea is to enable you to use 4 different pieces of software: MATLAB, SolidWorks, COMSOL, and Abacus. And all of these 4 are fundamental now in the real world applications of mechanical design. So since it's going to be, the software has some tricks in it and have some tweaks, sometimes you might run into issues with the appropriate mesh that you use, or maybe fillets that are not connected properly to tangent lines that can result in glitches when you do the finite element analysis and you build your code. So you'll see that there are technical aspects of that need skills. And the skills, what we will do is we have a forum online, and the forum is to encourage each one of you to maybe ask questions related to the software or the implementation, and get answers from others who have similar experience. And myself and the TA, Andrew Sheng, will be in the forum to help along and to give comments on how to deal with these glitches in implementation of the software. This way, we will be able to gain the experience. So this is the main projects, 25% of the grade. And then we have the gearbox project. And the gearbox project is we have 1-page specification of the requirements of the design online. I will show that to you. And this specification is that we have input shaft with a given horsepower and torque, and the output shaft we would like to find out at a given speed, and then the output shaft is required to convert that speed to another speed. So that's the idea of the gearbox. And you can have many different configurations, intersecting axes or parallel axes or inline. So we have a specific requirement, and this project is to be done mainly by MATLAB. So you have MATLAB availability, so you can code the equations and get the solutions and get your results. And at the end, you should be able to do a SolidWorks visualization of that gearbox. So now this project is not going to be starting until first week of August. The reason is that up to that point, you will have not had the experience to build up all of the elements that go into the second project from the course. So by past the midterm, then we would have some of the elements already in place. like deflection and stresses and so forth. And we will be able to follow an example, excuse me, on building this final project. And then we have also the final, which is 40% of the grade. So it's not like a major part. It's less than 50% on purpose. So you have a good part of the grade on the two projects and on the homework assignments. So if you do that systematically, you'll get the majority of the grade. And then the part that needs reviewing, memorization, and solutions and so forth would be in the midterm and the final. So what will happen is that the midterm will be based on the homework assignments and similar problems. So it will be similar to the homework assignments. Of course, it's not going to be out of homework assignments directly, but similar. And the midterm is going to be closed book with allowance for 2 pages of your own summary. So you can write your own summary of the equations, and that will help us study on the key equations, and then we'll take that to the midterm and use it to finish the test. And then on the final, as you'll see now, the course is going to be progressively more empirical as we go on and on and on from the point of failure assessment, static failure assessment, to fatigue, to shaft design. You'll see that many more empirical equations will be introduced. So, and tables and charts, that's what the design world is about. So when we get to that point, in the final exam, you will be allowed to use an open book. So it'll be an open book exam, and you could use a hard copy, or you can use the electronic version, but you're not allowed to access any solution manual. So with that, I think your final exam will be based on all of the skills that you build throughout the course. So up to this point, it's kind of a review of what to expect on that course, and I'd like to see if any of you have questions before I move on to the next point. Are there any questions? Okay, can I just, yeah, can I get affirmation that you hear me?
I can hear you.
Okay, great.
I have a question too.
Yes.
So you're talking about using SolidWorks and MATLAB. Is there a way of getting that software? Because I don't have access to it.
Okay, that's a good question. And thanks for reminding me. As part of your tuition, I think you paid tuition, and I know the tuition is pretty expensive, but as part of that is that the school provides access remotely to these 4 important software platforms. So through CSNET is our computational management for computational resources within the School of Engineering. CES is School of Engineering and Applied Science. So the CSNET, they manage the software, and they have licenses, school licenses, and they allow students who are enrolled in classes to access the software. And at the beginning of the quarter, they asked me to request the software that I need, and I did request these 4 platforms, and they approved them. So they should be all online. And I think what you have to do is to establish an account on CSNET, and then you will be able to access the software remotely. And you will be able to use the software as if it is on your own computer. So the number crunching is going to be remote, but the visualization and the interaction and all of that will be on your own desktop.
Okay. So is there like a link to that website to set up an account?
Yeah, I will get into that in a little bit. So once I just get to the review of the manual for the project, it has some information there.
All right, thanks.
Okay. Now I just want to.
Question off that, if you don't mind.
Oh, sure.
This might be repetitive, but do we have to use SolidWorks, or can we use a modeling software that we prefer, like CATIA?
Good question. If you have access to CATIA, that would be great. I think you should, you can use it. I have no problem with that. So I'm not forcing you to use these four pieces of software. You could use CATIA, you could use ANSYS, you could use pretty much anything. But the idea that we have here is that the more training with different software, I think the more marketability you will have. So although you can use CATIA, but it might be worthwhile if you team up with someone else to use SolidWorks as well, and then you will have this on your resume.
Okay, thanks.
By the way, I wanted to see if any of you did you guys make any teams, because we wanted to have teams of 2 for the projects.
I have a team.
Okay.
I don't have any right now.
Okay. Yeah, so to form a team, the best way is to either through the sessions that we have on Saturday, and we would like to form the teams as soon as possible, or on the forum, you just kind of request that you would have a team member, preferably close by geographically, so you could meet at some point to review things, or remotely if not possible. So I'd encourage team forming as soon as possible to get started with the project. Okay, so now I just show here the website. I'm sure that you've looked at it, but it's worthwhile just to go over what's involved in here and how it's structured. So we have a tab for the project, and the project has 3 tabs. Connecting Rob project, this is the progress report, and if you click on Access, you find that it's available July 11th, which means that you will be able to submit a progress report in there. If you just click on the tab, you'll see that it is due on July 20th, like you say here, at 11:55 p.m. And then you will go to submit your report. It should show somewhere in here. And then once the report is submitted as a PDF, then you'll get feedback on the report, and you'll pick it up from the same location. So the Connecting Rob project, because it is structured with a manual, then it has a progress report and has a final report. And those are, I'm going to explain the grades on those here. And then we would have the power transmission project as well. If you see the access here, it is a little bit later, so that we can be organized and start that at a later date. The project, I have videos, tutorials, and the tutorials, that the first one here is already available. It's after June 29th, so you can access that. And the tutorials, they say part 1 through part 7. Some of them are repetitive, but they basically go over the manual and explain the details of how the techniques that we use to implement the project. And then for those who are not familiar with COMSOL, I have provided COMSOL manual here. So if you click on that, then you'll see the entire manual. You can download it, and it is a good reference for COMSOL. And then we have 4 different tutorials that I put together on using COMSOL in general applications. So this is not particularly for the project, but for similar tasks that we use COMSOL for. And it's kind of worthwhile if you have the time to go online, and there's a lot of YouTube videos also on COMSOL and other applications to get familiar with the software. The project material that we have the power transmission project here. So if you click on it, then it is like a single page, and the single page is talking about the requirements. So we have A through I requirements to design gearbox, and the gearbox is 25 horsepower, and we have input RPM of 50 RPM, and the output is 2500 RPM, and so on. So this project, we want to prepare 10-page report and the appendices, and the appendices would be the MATLAB code that you wrote, and also the either sketch with SolidWorks or any other software that shows the selection of the gears and how they're assembled and shafts, and some of the details of the visualization. So this is the power transmission project. And then the connecting rod project, the access is July 6th. So this is right after the July 4th holiday. So if you click on that, you'll see many different items. And you will need some of these items as you build your project. So these attachments here is a folder for attachments and a folder for the manual itself. So the attachments are all MATLAB attachments, and the MATLAB code, because some of us are very good at MATLAB, some are not, still learning. So what we did, we wrote part of the code and then let the other part for you to fill in, and this way it will be a quicker learning experience as you build your code. And these attachments are attachments to the manual. So first is beam analysis. Connecting rod is going to be looked at as a beam, and the beam is under bending and under some tension. And there's a code here that's partly written to analyze the stresses in that as an initial step to select the sizes, because we have to do some sizing manually first before we do the actual model in SolidWorks and COMSOL. And so on. So you have some of the data here, for example, combustion pressure, the combustion coming from the engine. It has a certain pressure profile. So that profile is digitized here and then read into the COMSOL as forces on the connecting rod, and these forces bring in reactions, and therefore you would have a stress state in the connecting rod. And then some other elements for analysis, static like Soderberg design, and fatigue, as you see here in there. Now the manual itself is, we have the project here is called Project 2012, the manual. And this is the main manual. So if you click on it, you will see that you can download it, as I'll download here. And that manual is comprehensive, so it goes through step by step in the design. So now it is downloaded, and if I open it, then it will show that, let's see here. So it will show the manual itself, um, as you can see here. So the manual, it has like tabs in here, like you can click on what is involved from load analysis to preliminary design, 2D solid model and console, finite element, fatigue, fracture, and design optimization. So all of these are the elements in this manual. So the manual itself is was reviewed last in 2012, and right now Andrew is revising it one more time, and we will be updating the manual shortly. But by and large, it is it will have the same exact elements, but maybe some changes related to the new revisions in the software, because the software console, for example, has the new release is 5.2. So we will be changing some of the commands in console in there. So as you can see, the manual, what I'd like you to do is download it maybe this weekend or early next week. And then you go chapter by chapter. So the first part here, load analysis, you start from the loads, and you have a documentation of how to compute the loads on your connecting rod. And then you use beam theory, which is by hand or by MATLAB. And then once you kind of get an idea about the shape and the size, you will build a 2D model in console and do the analysis in console. And at that point, you would have like the chance to submit the preliminary report or for the project. And then the next part is the next few weeks are going to be improving this 2D, applying failure criteria, which we learn in class. Apply fatigue, fracture, and then optimize the design, change shape, change size, so that you can get the correct factors of safety. And then finally, before we end the class, we will have a chance to use Abacus. And that is, some of you will succeed, some of you may not have the time, but Abacus is another software that is used in the industry, and that gives us more opportunity to gain experience. So this is like an overview of the project manual, and we will follow that for our designs. So I wonder if anybody has a question at this point. Okay, so let me see, where is the share? Yeah, I think this is the sharing. Yeah. So back now to the requirements. So if we go now to that gives now an idea about the project. And then if you go week by week, for example, week 1, all of the weeks are very similar. You have the lectures. You can download these lectures, and these are just hard copies from the book. And then associated with these lectures will be the videos that explain the lectures. You have videos and they have titles, either introduction, material. So they go exactly with the chapters in the book, chapter 1, chapter 2. And then we have a homework assignment in which you will submit here. So homework assignment number 1 is going to be on material selection, and it's going to be on tolerances, and that will be submitted. So if you have here, if you click on homework assignment number 1, then you see that it is due on July 6th for this course. So this is the general structure. And now I just wanted to show you the grading. So the grade, if you look at the grading scheme, you'll see that you have homework assignments here. So we have 7 of them. This is 7 up to 7. And then the total will be up here. That is the 15%. And then we have the connecting rod final, and the power transmission, and the connecting rod progress report. And then the project total will add up all of this. Then we have midterm, and then the final grade. Now, what I wanted to mention is that the homework assignment says 7, but then you can see homework assignment 8 and 9. So there are homework assignment 8 and 9 related to shaft design. And since I stopped you from turning in homework assignments until homework assignment 7, the reason is that this gives you more time to work on the gearbox project in the last few weeks. Therefore, homework assignment 8 and 9 are going to be online still because they'll be important for final exam. But in this case, if you turn them in, it's optional that you turn them in. If you turn 8 and 9 in, then you have extra credits. So homework assignment or extra credit given for assignment number 8 and assignment number 9 to be added. So if you don't turn them in, that's no big deal. You can still read the solutions and prepare yourself for the final. But if you have time, you can solve them and then turn them in. Gives you more chance to be ready for the final, and then you will get additional extra credit. So that's the grading scheme in there. And in addition to this, before I leave this site, to familiarize you with it, the projects themselves, if you go back to the project, we have the connecting rod project, for example, here. It has all of the instructions here, and then you can see towards the end, there's something called project template. And this is a document. So if you download, this is a Word document. So you download it. This document is a template that will help the team fill in and make it into first a progress report, and then after the progress report, it becomes the final report. So if you look at here, this is how it looks like. So the template, you put your name here, and so it'd be like final report or progress report, and then your last name or last name of the team members. This way, we'll be able to identify the file with designation, if it is final or progress, and with the last names of members of the team. And if you look at it now, that it has a structure, so it has the grading system is clear, how much on abstract, introduction, load analysis, and so on. As we move on, we fill in these items, and it has a table of contents. So let's see if we can make it a little bit bigger here. So the table of content gives you what is needed, the items, abstract, the list of symbols, introduction, load analysis, and so on. And therefore, you will fill in. So if the abstract here, then it says the author should summarize the report, giving brief details of the project, objectives are important, principal conclusions important, and it should be brief and self-contained between 150 and 200 words long. So it's kind of very specific of what is professionally required to fill in the abstract. And that applies to other sections in the report. So what is the introductions? So general use of the connecting rod, discussion of variation of connecting rod, and so on. So you'll see that as you have guidance on filling in every item of that report. And I wanted to emphasize that this template, you will use it for the progress report. And then when the progress report grows a little bit bigger and becomes complete, then it turns into the final report. So it's the same thing. First, you submit the progress, get some feedback, and then you build it up to be the final report. So that's on all of the website. And now I just wanted to spend a little bit of time, we have like 15 minutes or so, to talk about some elements of material selection related to the homework assignment and stress and strain analysis. So if we look here in material selection, let me just get this out of the way. You see that we select materials based on their basic properties. And for this particular course, the properties we're interested in are generally stiffness, which is related to elastic modulus, density, because we want to have lighter materials in some applications, and strength. So these are the three things that determine our selection for materials. But the general field of material selection can cover many other things, as we'll see in 296B. We will get into thermal properties when we go to high temperatures. So here, the method for material selection is based on Ashby charts, and the Ashby charts is a plot of the property that you are interested in. Like, for example, the elastic modulus. Young's modulus determines the stiffness. So you plot the elastic modulus versus the density. And the density can vary from very low density, as in porous materials or foams, to very high density, as in refractory metals or ceramics. And the Young's modulus also goes over many orders of magnitude, as you can see here, from flexible polymers, rubber, and has very, very low elastic modulus, all the way to on the order of GPA, 1000 GPA here. That's extremely high, but generally several hundred GPA for some of the stiffest and hardest materials on Earth. And then you see that the classifications of materials, they have these bubbles, and the bubbles are like families. So you have a family of foams, polymers, you have elastomers and polyurethanes down here, and then you have natural materials in the middle part of this, and then you get into composite materials up there, and then we get into the two main material classes that are used extensively in engineering, that is ceramics and metal alloys. So the selection is based on maximizing some property, and it depends on application. So if I have, for example, an application in which I'm trying to maximize the stiffness in tension, then it turns out to be that I need to maximize the ratio of E over rho. E is the elastic modulus and rho is the density. So I want to have the lowest density and the highest elastic modulus. And that is a line of constant value of E over rho, which is this dashed line here, of a certain value. Of course, you can find that value if you know any coordinates of any point on the line, because on the vertical you have the elastic modulus, on the horizontal you have the density. So you can get the value of E over rho on that line. Now this line, as you increase the value of E over rho, the line, you have parallel lines. So I have another parallel line, a third one, fourth one, and so on. So each one of these parallel lines has a value of E over rho that is progressively larger and larger. So if I want to maximize the stiffness with the lightest materials, that's the objective, then I find the value of E over rho that has the highest magnitude, which is any point on the top line that you see here on that design. So if you have a top line, you'll see that it goes through some titanium alloy, silicon carbide, silicon nitride, so some ceramics and some metal alloys, and that would be the answer that you're looking for. Similarly, if I want to maximize deflection for bending, then the result is to maximize E to the 1/2 over rho. And I have the equations explained in the videos, but that would be a different slope, and therefore you have a different number of parallel lines that you will select the maximum for all of these. So this is the idea of material selection that we have it here. Okay, so finally here, and the remaining minutes that we have, I wanted to explain the idea of true stress and true strain, and how you obtain that from engineering stress and engineering strain, because we have a homework assignment problem, and several others will follow, come from that perspective. So as we know that the stress strain curve is generally given as elastic part, and then you have the plastic deformation, and if we define the stress as the force divided by the original area, A0, and the strain as a change in length, L minus L0 over L0, then this definition assumes that the reference state is the original shape of the material, meaning that the original area A0, original length is L0. And that we call the engineering stress strain curve, which is the most common that we have. However, as you stretch the material, the cross-section decreases, so A0 becomes different, and also incrementally the strain, the length changes as we strain the material. So for that we define true stress meaning the force divided by the current area, the current meaning the area as the material is deforming. Not the reference state, but the state that is deforming. So we call it sigma prime, so the true sigma prime. And the true strain is change in length divided by original length, but incrementally at the instant that you're interested in. So it turned out to be now that the true strain, we're going to call it delta sub t, or delta. And it is the sum of delta Li over Li, which turns into an integral. And that gives us natural log of L over L0, which gives us natural log of 1 plus epsilon. So this is the line, this line that you see here is a relationship between the true strain on the left side and the engineering strain on the right side. So if I have the engineering strain epsilon, I plug it in here, I add 1 to it and plug it in here and take the log, and that gives me the true strain. Now how about the true stress? True stress is sigma prime P over A. So I can write it P over A0 times A0 over A. P over A0 is sigma. A0 over A I don't know what that is. So I'm going to use conservation of volume, meaning A times L is the same as A0 times L0. And therefore, I change A0 over A to L over L0. L over L0 is the exponential of delta true, because we know that L over L0 log, natural log of L over L0 is equal to delta, which is the engineering or the true strain. Therefore, L over L0 is e to the delta. So in other words, I can calculate sigma prime if I know sigma and L over L0. And L over L0, I can write it as 1 plus epsilon, for example, here, from the engineering strain. So the upshot here is that there's a problem in the homework assignment that you apply these two equations. First equation is a given epsilon, find delta, and given epsilon and sigma, use this to find sigma prime. So you can rebuild. In other words, you given all of the data on the engineering stress strain. You put in a MATLAB code. You write these two equations. You put these in vectors or array, and then you apply these two equations. Then you should be able to recover the true stress strain curve that should be continuously increasing, as you can see in here. So that's basically what we wanted to discuss today. And there are other things that I will discuss next in our next session, and we'll solve some additional problems to kind of emphasize the homework assignments and to reinforce it. So I think I'm going to stop the sharing here and ask you for any questions that you might have, or any comments or changes. Maybe you want to change the time, maybe any other thing that you have in mind before we finish here. So are there any questions? Are we all good?
Hey, can we use this time to make groups?
Yeah, definitely. That's actually what I wanted to do. So, yeah, so let's just go around and see if everybody has a group, because that saves you time just gonna look for somebody. So I can see. Let me try to get the participants here. Just one second. So I have here. I guess, is this Mike Bass?
Yeah, this is Michael.
Okay, so do you have a like a project teammate or a group already?
No, I'm in St. Louis. I'm in the Midwest. So if anybody else is in St. Louis, that would be great.
I got a couple of communications for people in the St. Louis area or on the East Coast. So I'll send you, like, maybe I put it on the forum, because they said that they were not able to participate because it was like lunchtime and they had some other commitments. So I'll try to connect you with those.
Okay.
Yeah. Andy, do you have any teammate there?
I haven't paired up with anybody. I'm in the Palmdale, California area. If anybody's out there, that'd be great. If not, doesn't really matter. I can work with anybody, no matter where they are.
Yeah, it doesn't have to be exactly in the same geographical area, because we can do very well using Zoom, and we, just remotely, we could also do our work.
Right.
So anybody in California who is close by to Andy?
This is Catherine. I live in Santa Clarita.
Oh, that's really not too far then. So Catherine, can you pair up with Andy?
Probably. Andy?
Yeah, that'd be great.
Okay.
Yeah, so maybe you guys can just, communicate. Everything can be done remotely, but at some point, maybe you can just have like a short meeting to discuss progress and so forth. That'd be good. Christian Calvo, where are you?
Yes, I'm also in Santa Clarita, but I do have a team member already, so I'm good to go.
You're good to go? Okay, great. Okay, Cody Cooper.
Hi. I don't have a teammate. I'm actually in Santa Clarita as well.
Oh, okay. Yeah, so that's good. I think this is great. So you have a teammate already?
I do not have a teammate.
Oh, you don't have? Okay. Anybody else close by to Santa Clarita or Palmdale or maybe San Fernando Valley? Okay. So anyway, I think you can maybe put it on the form, Cody, just to see if somebody else can team up.
Sure, absolutely.
Haley Smith. Haley, are you online there? I'm not sure.
I'm here.
Okay. Do you have a teammate?
No, not yet. I was gonna get online and post to the discussion thing.
Okay. All right. I don't know where you are. Are you in the St. Louis area or where are you?
Yeah, normally I am. Right now I'm in Indianapolis,
Okay.
but normally I'm in St. Louis.
On the East Coast. So I think on the East Coast there was maybe you can team up with Andy. Maybe I'm not sure, but I'll leave it up to you guys.
Okay, perfect. Yeah, I'll just post on the discussion.
Yeah. All right.
Thank you.
Yeah, and then I think Jim Snyder.
Yeah, I'm here.
Do you have a teammate?
No, I do not. And I'm in Rockford, Illinois, which is not too far from Chicago.
Yeah. Anybody in the Midwest? Yeah, it might be hard, but I think we can all team up online. Yeah. Robert Heng, do you have a teammate?
No, I don't have a teammate yet. I'm actually in like Orange County, Costa Mesa area, and I work in RSM if anyone happens to be around there.
Yeah, you might want to consider teaming up even, somebody, a distance away is okay, just online.
Yeah, I figure as long as we're in the same time zone.
Okay, so I'll leave it. And Samantha, do you have a teammate?
I do not have a teammate. I'm in Denver, Colorado.
Oh,
so not near anybody.
we have a very diverse class. I'm very happy that we have the whole world just right here from all over the country. Great. Anyway, so I think I just wanted to stimulate the discussions and the interactions. I'll leave it, for you guys have a great 4th of July, everybody. And then just keep up the communications and please just make up your teams as soon as possible because that would make it easier for the progress of the projects. Okay? All right. So I think we'll end our session and have a good 4th of July and we'll see you next week.